I'm allowed to talk. Okay. So my name is Vahan, I work at Capital One. I lead our statistical data sciences team. We are different data scientists that specialize in modeling, experimental design, pretty much anything that is stats. Capital One is a company, as you know, we're both expanding in the US and me personally, my background is actuarial science, which is a little different than I guess what typical data science comes from. I like to consider myself a reformed actuary, so I passed some of the exams as well, and I've done some internship as an actuarial analyst. I was blessed to be able to go to the University of Waterloo. And so we have something called a law program. We get to try a whole bunch of internships in 4 months. So kind of get a feel for the marketplace and get some experience. One of my overturned children were as a analyst. It did take me a while to reflect on myself and realize that it's not. And again, no offense to actually out there. It was my cup of tea. It's an accounting. It's block 8, and it was not long for me. So, anyways, I pivoted and I doubled down in statistical analysis specifically. So, what's the point of this talk? The title suggests that it's about an application of machine learning, which it is. The way I've structured it is I first want to have a discussion, and hopefully I can engage you guys after a little bit. It's just to try to find some common language and get a sense for how people define certain buzzwords that are ever so prevalent in the market. I personally think that most of us do different things. On the same machine learning, big data, deep learning. And so I want to know what you guys think about this, what it means to you, and then I'm going to give you my opinion in terms of what I think it means to me. And then I encourage you after the presentation to talk to me, and let's talk about this. This is a very silly picture. It's supposed to provoke a specific buzzword. Machine learning, that's exactly what it's called. Now, I can definitely that sounds it wasn't really immediate hit. But the point is, I think this in some way does represent the way interpretation, or at least what you get from the headline article of what machine learning is. It almost portrays machine learning as a bunch of sentient machines or almost like general AI. And we could pretty much give it any problem, it'll kind of figure it out and the answer. Which, is far, far. But I think it goes beyond that. I think when people say machine learning, it can mean several different things based on the whole ecosystem and the model pipeline. It could be just a learner, or it could be always some data and so that being said, let's talk about where the source comes from. So I'll give you a second to read that. Kind of small. It's classic over. What it says is it's essentially trying to make fun of the fact that big data is everywhere. It's this big, scary, ominous thing. It's got unknown powers. It's the future. If you harness it, you will rule the world. If you don't, you'll be left in the dust. And anyone that works in the private sector, I'm sure at one point or another has heard management refer to big data as something almost magical. And so I want to talk a little bit about this as well. So starting with the first side, actually, what does machine learning mean to you? Raise your hand and answer, and I'm going to wait until I get an answer. Yes. Okay. So pattern recognition, supervising problems, essentially getting a computer program or algorithm to be able to find such patterns on its own. So that's kind of that's definitely accurate, and it's a kind of a learner-centric definition. Anyone else have any other interpretation? Yes. So maybe go on with data. Okay. And then talking, I think more for the streaming data or constantly Fair enough. I mean, trying to do human intelligence. All right, what's big data? Here. Okay, and can you give us some type of yardstick to figure out what is the threshold of volume or velocity or veracity for you to declare this is indeed the biggest of data? You're seeing something. So do you have like a petabyte threshold? What if I had a petabyte of a million null fields and one field that says meow on a billion times? I don't think they fun. I'm just asking. It is tough. There it comes in all kinds of different forms. There's different amounts of information contained in data. Okay. How about let me give you kind of how I visualize the entire, I guess, life cycle of a typical data science project or a machine learning project. I'm going to use this to kind of frame what I'm trying to get at here, and then I'm going to follow the excerpt from paper and then the case study. But if you'll bear with me, this is kind of how I think in my head data science could potentially work. I put the labels data engineering and data science. Don't think about all this arbitrary. It's a matter of opinion. To me, I'm going left being more kind of the data architecture and the platform where it comes from. The right way to get that actionable insight based on learner. And of course, this is a complete way to blend this together. But how we typically get to the machine learning applications, we have the source data. It could be a bunch of data from places. It could be a relational database. It could be unstructured data. Who knows? Usually, at some point, if you're working with a company, there is a source of aggregation, kind of the starting point of your analysis. Where the data originates from. And then at that point, you start approaching more to machine learning. So there's a sanitization. You extract the data, you prepare to transform the data shape they need it to get to extract and apply the labels. Problem. Then they can get a feature creation. And at this point, it starts kind of measuring with the learner. You can create features in order to test with your learner, and the learner itself can create features. But this is kind of a back and forth, which then you create more optimal classifications or predictions. And then from here, the outcomes. If it's a self-learning model, then it'll keep backing, it'll keep improving. And then everyone gets to the end in terms of your output. Then at some point, there's a way for this data to kind of go back to your sources, trigger some kind of treatments or strategies, and then that then becomes part of your source data and goes back. So I think it's a whole ecosystem. And to me, I'm not quite sure exactly where machine learning begins or ends. And we get different answers where we talk to. Tech companies tend to focus more on this entire system as a piece of software, so for the tech approach to it. People like companies these days tend to focus more on the learner specifically, but that's also the algorithm that can identify different patterns and make learning points. People that come from more the data architecture background, they can be entirely concerned with how do I have a data platform that can enable extreme speed of this entire process, delivering that source data and being able to estimate my learner extremely fast. Okay, let's dive back into terminology for a second. What is this? Thank you. That's our looking for. But what buzzword comes to mind? AI, neural nets, deep learning. Here's the interesting thing. When neural net jumps out, it's kind of roast me. It's kind of with this romantic view of the whole concept as in we're actually the computer's evolving on its own and be able to do anything from the little source. I don't know if it's necessarily true, but again, if you look at the headlines, this is kind of the sense that you get to when people talk about it. But anyways, I think you guys seem to be fairly distributed already, so you're making my job really easy. Okay, so now we kind of have some kind of similar language. Let's dive into estimation paper. So this was published by an internal researcher at Capital One. So recently, it's nothing groundbreaking. It's just an interesting example that I like to talk about. So the idea was, let's look at different types of, we're focusing on the learner, different types of classifiers, and which algorithms do well in work in situations, and trying to get to the root of, what makes deep learning so special. And is it good at every single problem, or is there some kind of synthetic stuff that's going to do it? So the source of the data that we're going to do this small study on is the this data set. So they look at pictures. There are small simple pictures of 28 by 28, black and white. And the idea is to identify which digit this is. Right? To make sure for a human, it's insanely complicated for a computer. Okay, so we're going to see different models here. Yes, the top is essentially linear regression, and you can do information on the in this situation. And surprisingly enough, the error percentage is only 12.6%. It's not that crazy, and it has over 500 parameters. So as you can imagine, if I have my long array space, 724, I guess columns, those are each of the pixels, right? In terms of geography and which pixels in order. And then it's basically pixel intensity, right? So there's about 300 parameters created from here. So you can imagine all kinds of stuff with essential raw variables and every combination therefrom. You can calculate all kinds of like velocities and all these trigonometric transformations and try and break this down into basically the I think it's something reasonable. That's not machine learning. That's kind of just what's up with kids, right? And I just wanted to mention that because hey, it's possible to get pretty far with proofs. It's just that you get an ROI based on how much time you spend on this. That's what machine learning improves. So in some way, the basic classification tree, which is a tree, and it's able to actually come pretty close to the regression. It actually outperforms, which is interesting. That trees actually do massively well. It's a big step change. So then we start getting to the territory of something more sophisticated machine learning. That's now the model average, right? So if you're working with flagging, it's essentially going a lot of classification trees, and then you average that. Right? And so it's on average, it's much better than a single. And then you look at, so now we get into H2O, and we're learning the kind of the big guns in terms of machine learning. So we have a shallow neural net, massive step change, and actually is excellent. This was kind of a lot of neural net that was done back in the day, I guess before the big boom recently. They usually start with shallow nets. It was just, it has something easier to estimate. And, theoretically speaking, even with one layer, you could still get, because you're still a universal approximator in theory. So, again, it's not crazy. And even here, there's, 560,000 parameters, right? And it takes almost an hour to estimate this. GBM, the little GBM. It gets some love in the Chicago circles. Some people are making huge fans. So it's H4 GBM. And if you're familiar with that algorithm, it builds tons and tons of truth in sequence. So you're predicting the errors of the previous tree. And so that actually does extremely well. And the algorithm is pretty good. That's interesting. And this is pretty much the standard setting. We just limit the depth of the tree to 7, and we let it run. And then the deep neural net does actually does the best. Surprisingly, it's quite a complex architecture. Well, it's not really about these layers, and it's parameters. So interesting, and it is on the bottom. It's the best kind of yet. And again, it's nothing even comes close. And then just for reference, like basically approximately human with super equals super predictive. It's just the theoretical best you could possibly do in terms of like if a human were to be the learner, how often would you make a mistake? It's so arbitrary, but the idea is like let's just assume that you're not going to get to 0 and the lower you get to that. Okay. So far so good. This seems to be in line with what we see in headlines. Learning is pretty awesome. If you add more than one in there, which is what so again, just more observations. Neural net is pretty much any architecture. Deep learning refers more specifically to more than one thing. Okay? So in this, again, we see this kind of in line with what we hear, and that's the deep learning. Okay, so let's change this up now. So in this paper, his hypothesis was that what deep learning is particularly good at is that it is extremely capable of thinking arbitrarily complex, and so the idea is though that it could potentially get bogged down with noise or it's all forward in there, right? And so the reason that this is of interest to fields like mine, for instance, which is in finance, we're dealing with a very noisy field of correlation between causal variables and if I'm trying to predict default rates a couple of years in the future, I don't know, I have your credit history, I have your income, I don't have a definitive, trustworthiness rating, or is this person a deadbeat? I don't know these things. Are you going to lose your job in the next year? Who knows, right? But we approximate these, and basically we look at the manifest variables, variables. So here we're seeing is like, hey, if we have an imperfect tensor variable set. So typically in image recognition, we almost have a definitive data set. We have every pixel pertaining relevant to that picture. So let's talk about a dimension. Okay, seems kind of crazy, but let's look at just one single dimension and whatever pixels kind of show up on that. You try to figure out what we're doing. Okay. So it becomes a little more of a verified all of a sudden. I mean, the LDA still kind of sucks. But you saw looking at all the more machine learning stuff, and this is more the single tree, but they're all pretty much the same at this point, right? Which is fascinating. It just seems that, I mean, obviously we reduce the amount of predictability in the set, but this is suggesting that when you're not dealing with a definitive set of information, you might not do as well. So here's another. The next step is then, okay, let's check a couple things. Let's create some hypothetical prediction surface. It's this way that as a function. Let's try two things. Just a stress test which machine learning algorithms are robust or kind of perturbations in the data. One is let's add a bunch of noise to it. So that's step A. Let's see how they do. The next one is, okay, let's ignore the true variables just to create the surface. So let's make those latent variables. Let's create 10 manifest variables based on random correlations with the true variables. And let's build a model using just these correlates and not actually use the definitive variable at the time. So interestingly enough, just adding noise doesn't do much. Deep learning is still robust to some level of random noise. It does quite well, but bagging does really well too, and GBM does really well as well. I think bagging is the best, even though it looks a little messy. But interestingly enough, again, when you're working with data that is, I guess one way to describe it is low signal noise. You don't have true definitive parameters for that very active interest. You start running into some trouble. And then other types of tree-based algorithms tend to be some trouble. Anyways, this is not by any means it's just I wanted to go over this just to kind of work your thoughts a little bit. It's thinking about there is such a thing as a one-size-fits-all algorithm. This is where people the right problem. Machine learning in general is very useful, but there's still a place for human in terms of trying a whole bunch of different algorithms. And also, even something like deep learning, getting the architecture just right, I mean, that takes a lot of either expertise in the area specifically or a lot of trial and error. So just keep that in mind. I'm going to stop here in terms of talking about, I guess, different types of theoretical things in some simulation. I'm going to do an actual case study now. I'll talk about how we've actually used machine learning to figure out. Oh, I missed the slide. So I wanted to call this. This was some machine learning fails lately. They're in the media. I don't think it's removed some of these. That's why it's actually very fast, where it's not. But that's different. That's just models aren't always infallible, so that's one to keep in mind. The other two was funny. It was somewhat funny. But the other two, it was just a good demonstration that it doesn't matter what your algorithm is, your data. If your data is biased or is insufficient, all you do is perpetuate that bias. And you're not going to solve anything. You can't create new conditions from that. we can do is converge to the best pattern there, but the pattern is not really missing or biased, not solving for anything. So we'll make something like a chatbot that would be friendly from bots to ultra racist, hateful, like 5 minutes of it. How could you not realize the internet can corrupt anything? Again, VAI, this what would you thinking? Objectively assesses machine learning, and then it systematically ranks cases into a column. So, anyways, data is the most important part, actually. So, that being said, let's talk about search engine marketing. There's a few case study real project we worked on. So if those who are familiar with how search engine marketing works, I'll explain the process. You essentially set up an account as an advertiser, you select a bunch of keywords or terms you want to bid on, you put in how much you want to bid on that, and then an auction happens when there's someone searching one of these terms real time. The search engine looks at who bid how much, as well as looks at something called a quality score. So they want to always make sure they have a good customer experience. So they want the ad to have some relevance to what the person's searching. Otherwise, you have to pay a penalty. So if you have a high quality score, you have to pay way less in this spot than if it's the low quality. And that shows up, user clicks on it, user goes to the website, user applies. Okay? Any questions? Cool. Okay. Yes. So yeah, so so this case study, we're looking specifically at who clicks on our ad, on that ad specifically that we bid on, nothing else. Okay. So how it used to be run was, we have our marketing team and we have our ads and we have a budget, and then we reach out to the agency. They use a third-party bid management platform. They have a team of experts in marketing. They have targets, and we just manage all this. And they push all the stuff and updates all the search engines in order targeting the account. Okay, what is that? So at this point, it was essentially very little optimization. It was all manually done by a third party. And so the question that we asked ourselves was, can we do better by leveraging machine learning, by automating this entire system, by bidding algorithmically, and no longer relying on a team of experts to manage this manually? So what we did was we told the agency, hey, we're going to do a test. We're going to hold down half the country. We're going to be bidding on those using our algorithms. You need to do what you did on the other half, and then we're going to compare notes. See who did that. Right? So, down here, done experiment, pretty straightforward. First lesson, we told them about this test. The next day, they improved their efficiency by 60%. It's called the sugar head syndrome. It's a hell of a water. And so we already started at a top place, and then they just massively go their efficiency. They're trying their absolute best. Every member they try to do whatever they can to run the most well-run campaign anyone has ever seen. They want to keep the business, right? So we get the data and we get the bids. I mean, we get a dump of what they're currently doing, like over here. And then they do this, and we don't even necessarily know what they did here. We got to start from here. We got to match this. And okay, so we get the data. Go to the first preliminary model. Nothing too fancy. It was actually mostly regression based, doing some basic text mining and whatnot. And we could basically develop the model to predict the likelihood to apply. Ideally, or some on that. Your break-even is higher, you can afford to spend more because you can get more. And so you can kind of see what the break-even bidding amount is, the more likely someone is to convert. And then this can kind of expose if they're bidding efficiently, because we know this is the break-even. So if they're ever, so this is actual cost, so they're running the campaign. If ever it costs more than break-even, which is hemorrhaging money, right? So this is how it used to look. And brand is people that search specifically it's less interesting because the farms are so high. It's kind of like, even there, they're spending a ton of money, overspending their customers. And then again, just underscoring the efficiency improvement after we made the announcement of the test, they improved extremely well the profitable across the entire range of people working. So the idea was essentially they were already doing pretty well. So we had to really get fancy and double down and see what was the best possible data optimization algorithm possible in order to make it better or not, and see if we could scale back the efficiency beyond what they were able to. So that's what we did. Just put some random, not exactly. So I just put some random features algorithms. So basically, we did what's ever some algorithm based on ensemble modeling. You know, the most maybe combine all of it with another algorithm, and then that kind of, on average, does perform way better than each individual model, at least in general. And so we kind of threw everything they teach us at the same, and basically kept going at it until we get to a point where we could start to identify lost pockets of inefficiencies, even when they're the best forward under threat of getting fired. And so this is where we ended up. So I'm looking at this as a classification problem, but we're using Gini index as a performance metric. I don't know if this is a metric, you look at ABC or KS or something like that. But we're looking at Gini, the higher the better. Zero. And so this is kind of what we started. It was the regression. And this is kind of how the vendor was doing. So the more you slope steeply, the better you're doing. And then we did an ensemble, and then we started doing way better, smooth across the range. And then you could basically convert that to where you're willing to pay more and where you're willing to pay less. And then essentially, as this model keeps refitting and keeps re-optimizing, you keep updating your bids and you keep making sure you're on your below efficiency frontier. And so what that lead to? So not only did we meet their efficiency gain, we actually beat it significantly. So we're able to perform a lot better than what humans are able to do. Once again, isn't too surprising. It's just, you know, when someone improves that drastically, you get a little nervous. But unsurprisingly, algorithms prevail. And so we're able to run something with the undying discipline and you know, machine learning precision, literally machine learning algorithm. You know, still not getting keyword, you know, going on. We watch this kind of what performed best most recently, to forget about what they've done historically, and that kind of stuff. So, yeah, all around the success story. And then just to get some of the metrics of how the campaign improved over the course of the test. Again, quality score shot up massively. That means on average we're putting more of ads against more of ads in front of users who care more, click on more, we're not getting more. So then it becomes a virtuous cycle, and the ad becomes irrelevant, and then your cost gets lower and lower and lower. And you can see the weird thing, and then that's kind of funny. It's almost like typical of humans where they try really hard to get a little lazy, try really hard to get a little lazy, try really hard. Okay, so what's the lesson here? The lesson here is I don't know exactly what machine learning is. I don't know exactly how to find it. To me, I think this is kind of a reasonable definition of it. I think what most people mean, and I think how you should think about it in terms of making robust is think of this whole system here, getting all the data, putting it in a common format, running it through the cleaning and the patching of the data and the appending of labels or other relevant information, and then constantly creating features, updating your learners, and updating your evaluations, getting your outcome, applying new bids. So human oversight is always, we're not Skynet just yet. We can at least look at it once in a while. And then you keep it back in, you push it out, and the cycle keeps going. So I think this whole ecosystem is probably better about it. It definitely makes sure there are no blind spots, and crisp for as long as you need. That's it. That's all I had. Guys have any questions? Right now. Otherwise, we could come. Yes, I mean, so in at least previous paper for the machine learning and distribution, we use the HTML software for that. Yeah. Everyone uses very strong. Yeah. Right, okay. So he asked, what's our history strong? She was asking how we were able to define the country for the test. Ideally, you want to randomize at the individual level. It's messy with IPs or cookies for exchange. So basically, we did just a little scramble to that. The best we could randomize. So we can actually pull that out and specifically we could do it way more. Yeah, so we have a fixed geography. So these are the geographies we're playing in, and we're also touching it. We're continuing getting data, changing our strategies, getting new data. So she was asking, once it was held out, was it the one snapshot we dealt with, one little test, or we continue to get new data and try to get it? The answer is yes, it was possibly yes. It's a win-win story. They're a very good company. They're doing just fine. They just don't have us as a client. Yes. So, question. This, I mean, not, I mean, we say reinforcement learning, I almost think of like a specific neural net architecture, but like it is reinforcement learning in that we're constantly refitting as we push new bits, we get new results, and then it goes right back. And so every bit cycle, it's on a couple day cadence. Every all the estimates, all the models update, and we push brand new bits out, and then that causes difference in performance, and then that comes back in. So what? So you asked, well, what's the? So first, is it kind of reinforcement? Is it going yes. The ag section is what's you looking for. I mean, again, you're running a business. Issues are precise. Issues happen. Data errors. Certain part of the data have like breaks. Layout changes in the file. You get crazy values somewhere. You still want to look at this thing and say, hey, is it saying right now? Is it saying for the next thing we shoot $1 million for a cook for search of like down and so it's mostly just to get a sanity check and to see if it strategically aligns with what you don't want to do. Cool. I guess that's it. Thank you so much. one purchaser brought it and stuff here. Wow. They come in and like all their hotspots and stuff like that.
Hello, guys. All right, I'm going to get started. So, we're start for Ashrith. The second session, what's going to be me? So, my name is Ashrith. I'm a secondary scientist at H2O. We've come all the way from San Francisco to tell you guys how we handle anti-money laundering. How we create anti-money laundering solutions. Quick poll before I start off. How many of you guys out here know about H2O? Can you give a quick, raise your hands? Okay. How many of you guys have tried H2O? Okay. 2 more questions. How many of you guys know H2O is open source? Oh, that's actually a good job. How many of you guys know H2O is open source? Super. How many of you guys know that H2O has got algorithms ready to be used and deployed? Okay, pretty good number, but not enough. So what we need to do is, in the end, if there's a popular vote, we can probably show you guys, how to use H2O, like a quick 5-minute session. You can go home and have fun with it, and come back to us and email us and say what's wrong or what's right. So my talk today is about anti-money laundering. For one more question, how many of you guys know about money laundering? Okay, I'm probably in the right place. probably for the right reasons or the wrong reasons. So, one of the things that we do at H2O is we not only create algorithms and create a product, but we also try to create solutions, that by working with our clients. These things usually end up as products, and one of this anti-money laundering actually is on a pathway to a product right now. And we come up with really interesting use cases. My focus area happens to be cybersecurity or financial fraud, and the financial fraud AML is an important thing. So, okay, this is not working. Oh, there we go. So, money laundering is really nothing but washing all the black money or the ill-gotten money that you've got with legitimate money that could exist in your accounts or in any kind of regulated financial institution. It's basically trying to mix what all you got through the wrong means or unaccounted means. Just mix it up with your legitimate means, and then go ahead and say just prove that that's how it is. Much of the money comes from like drug trade, human trafficking, online gambling, and insider trading. And if someone else is wondering, what does this got to do with machine learning and AI, you'll get to know soon. So just hang in there. So what's the problem with this? Tons of problems. There are societal problems. Countries lose, lots of money because of a parallel economy. There are countries where the current government have been thrown out and alternate powers come into power. And illegal trade tends to grow a lot, which is in terms of human trafficking and drug trafficking. There are actually two good books if someone wants to read through. One is called Laundering, and the other one is called Illicit. Two really good books that talk about money laundering, so that might, if someone's interested. So our focus right now is purely to look at money laundering through banks. And one of the reasons this has become a big issue is because recently governments across the world have started to focus on tightening the requirements for money laundering. In the sense, you need to show, even if there is a very small amount of evidence that someone might be laundering money through their accounts, you're supposed to report it. It doesn't matter if the report is actually captured and someone is investigating or not, but it is a huge requirement now that you actually report it. And this is happening across the world, in Asia, in Europe, and of course in North America as well. And so there are tons of solutions that's coming up, that have come out actually. Most of them are rule-based, but I'm sure as most of people have looked through, rule-based solutions tend to have limited reach, because one of the things is rule-based solutions are stateless. They do not capture the intelligence that goes behind an algorithm. They are merely looking for thresholds and trips and stuff like that. But as these systems are not successful yet, one of the things that we can do is we can make these systems smarter. Now the question comes up is, how do we make them smarter? Like for rule-based systems, do we have this really huge cache, where the rule system tracks every user's behavior? Well, that would become a really big data set, and then it would be difficult for all of us. It would probably be a lot of data mining, and that's about it. But then that takes a lot of our time as well, and it's a lot of resources that are not necessarily being optimized for utilization. So one of the approaches that we use at H2O is we use machine learning to design algorithms that help us do it. Help us track laundering in a very interesting way. And as I think Vahan had just spoken earlier, he was using ML for reducing his cost of acquiring a user or a customer for that matter. We basically are using machine learnings to reduce the number, to be able to identify this behavior. Now, one of the ways that we identify this behavior is the idea of machine learning itself, is where the programs or algorithms, actually, these are not necessarily machines, it's more conceptual, it's more like the programs actually learn from the data itself. And a higher amount, the higher number of certain events actually means that the algorithm or the program or the machine in this case has a higher probability of learning that behavior. And then once you're testing it, then recognizing that kind of behavior is a possibility with a certain higher amount of probability. And that's one of the reasons machine learning is heavily dependent on the amount of data set that you provide. So, which is actually another reason, this is going to be just a very small tangent, is that when you necessarily do outlier detection or anomalous behavior detection using an out-of-the-box machine learning algorithm, you don't necessarily see the results immediately. And that's exactly for this reason, is because you don't have enough probability probability of the data that you're trying to identify through your algorithm. So does more amount of data means you have a better algorithm? Kind of. I mean, one of the reasons I say it's fundamentally a yes is because more data does mean that your algorithm has the potential to perform better, but it does not mean that it will. Primarily because your algorithm needs a really good set of features. Now, only if you have a really good set of features, then you're capturing the essence of the data and you're providing that to the algorithm to learn. And that is where the feature engineering is actually a very important process of machine learning itself. So one of the core areas of focus that we do, while designing algorithms like this, is actually feature engineering. So I'll take you through a use case with respect to money laundering itself, and I'll show you a small set of examples of features that we engineer, just to show how things make a difference. So one of the use cases that we work with is to identify quick or excessive cash withdrawals using ATMs. Now, does anybody want to take a guess as to why this might be an interesting area in money laundering? Just give it a try, yeah, please. Okay. Sure. Okay, that cash itself is a lot harder to track, which is, yeah. Okay. So there's a good consensus about how ATMs actually play into the whole money laundering process. Cash is actually one of the core focuses of money laundering everywhere, because cash is unaccountable, it's not trackable. Electronic money is actually very easily trackable, not physical money. And which is why this happens to be one of the largest use cases that exist for money laundering. The reason ATM tends to be one of the primary focus areas is because money can be moved very quickly in small amounts. So if you look at your rules engine, your rules are usually set up as, oh, did this person draw $2,000 or more this week? Did he draw $2,000 or more for the following week, and so on? So they track for about 2 or 3 weeks, and if it's above a certain threshold, then that account is flagged. But now, do you guys think there will be a situation where, let's say, you draw about $1,900 every week, and then do you think the rule system would actually flag it? I'm pretty sure the answer is right there, but I'm just checking. Probably no, right? Yeah, so that's exactly what happens in the rule system. So if you draw anything below the threshold, it actually never flags it. So I could be literally moving money $1 less than the threshold, and that would be still fine. So, which is why rule systems with ATMs is usually a huge trouble. And the other thing is, there is this concept of money mules, where people and their accounts are actually used to move money. So let us say, I have a friend who deals in drugs. I don't. Let's say I do. And he wants to move probably like $10,000 or something, from his drug earnings to somewhere else. So he'll say, hey, can I use your account? You've been really good. Your credit score is really high. Can I use your account, so that no one will suspect you, to move this money in a span of 6 months? Okay, he'll say 6 months, and I'll be like, oh, 6 months is not going to be a problem because, I'm smart enough to know that the algorithm won't flag it, and I'll say yes. So I'll give him my credit card, my debit card, and I'll say, yeah, you can deposit it. So what he'll do is, instead of moving the money in 6 months, he'll probably move it in 2 months. Now I've been flagged. Now, because he moved money faster than he said he would. So in that situation, I'm actually the money mule. So that's exactly how money mules work. And sometimes what happens is, this friend says, hey, I'll give you 10% of what I'm moving, so like $1,000. Now, will you allow me to move the 10,000? Then I'll definitely agree, because I'm getting $1,000. So that is a very common situation as well when people are moving money using ATMs. Now, these are the kind of activities that usually happens. These are the kind of ways in which people tend to move money. But there is another situation. Now, when someone is moving $10,000 through my account, if the system is seeing that I've been I usually hold about $5,000 or $6,000 or $10,000 all the time in my account, then I'm not that big a suspect, because mind you, this is still going through a simple rules engine, and then there are investigators behind this who are sitting and analyzing the system. They're saying, oh, does Ashrith usually have this much amount? Oh, he kind of does, so this might be a legitimate money that he's moving. But now, if I almost always end up having like $500 to $1,000 in a month, then moving 10,000 would definitely raise some flags. Which is another reason why this kind of movement is actually very easy for investigator to identify, but not necessarily for rules engine. There is another situation as well. Sometimes what happens is people tend to open up fake accounts. For example, someone who's traveling, someone who's visiting, for example, Canada or the United States from some other part of the world, comes in and with some fake identification opens an account. Okay, and then that account is used for moving money. Now the thing is, you have to remember is that when you do ATMs in those kind of situations, you're literally pushing the money out and then you're withdrawing it. So before the bank actually knows the part of the money is already gone. So these fake accounts or new accounts tend to cause a big problem. So, which is one of the reasons, accounts that are actually mature or, in a sense, have been associated with the bank for a long period of time, tend to hold a lot more value when an investigator is looking at it. So these are usually the general behaviors, how cash withdrawals, ATM is misused money laundering. Oh, I think I forgot to let you guys know, if any of you have any questions, please stop me right there. I would love to answer your questions, not a problem at all. Please, yes. So, when you say, what do you mean by real money laundering? Can you explain that? Yeah. So the $1,000 or the $10,000 is actually just an example. So people tend to move. So the range of money that we've seen move is probably in the thousands to close to about hundreds of thousands. Actually, I would almost say probably in a few millions, but that's happened over a period of time, so we don't necessarily bring that into our fold. Does that answer? Okay. So yeah, so did anyone else have any questions? Okay. So the problem that we see in the current system is that the rule-based systems are usually very difficult to identify the kind of money movement that are happening right now. And the rule-based systems tend to identify only the trips. So if you draw or if you move anything that's about $2,000, so like 2001, then the system would trip, and then it would know that there's actually some kind of movement happening. But if you're to do 1999, then it wouldn't, and that's usually the issue with this. So anything below the threshold, it tends to miss it. And the rule-based system, as I said earlier, it's stateless. So there's hardly any memory. The only kind of memory it has is when it has to look for an alert, in a continuous fashion. For example, if it has a tag for any kind of money laundering, then what it'll do is it'll see if you've done a $2,000+ transaction, money movement this week. It'll put you into a cache, and then it'll wait for a week from that date on to see if you've done another $2,000 transaction to verify with the cache, and then it'll flag you. If it doesn't see a record in the cache, then it will just discard the record and you'll never be flagged. So that's to the extent at which the memory process exists with a rule-based system. So the advantages of using machine learning with artificial intelligence in this case, I think probably when I say AI, I'm probably a bit sketchy, isn't it? Maybe. So the machine learning systems don't necessarily depend on the threats that the rule-based systems depend on. They tend to learn from all the idea is that they learn the behavior from the features that you can develop. So this actually means that you have to provide great features for the algorithms to identify what kind of behaviors happen. And we also incorporate the feedback that we get from investigators and experts into the algorithm. So a lot of these experts tend to have subjective opinion about a certain money movement, but we tend to encode that into an actual feature, which goes into an algorithm, and that actually gives us a certain edge in terms of how good the algorithm performs. So this is, in a simple way of putting how ML can support my learning itself. So I'll give you 3 feature examples that we used while we were working with a few of our clients. And the reason why I've chosen these 3 is, of course, these 3 are the best. The rest were not that good. We're just messing. These 3 were some of the best that we actually had. So the age of the account, as I said earlier, is one of the most prominent features that we have in the algorithm. Because an account that tends to be mature with a bank tends to not commit these kinds of fraud. But on the other side, we've seen a certain behavior with old accounts as well. Anybody wants to guess what kind of a behavior it could be? Please. You're probably close to the ballpark, I can tell you that. So, anyone else? Maybe? Yeah? No, that's a bit far away. So, okay. So what we've seen here is dead people have actually come back to life. So someone who's dead, who's been declared dead pretty, in a rigorous fashion, has come back to life, on the banking systems, and that is just super interesting. So that's another extreme part of the data set that we have, that we actually had to, completely move out of our equation because they kind of cause trouble when they with the algorithm. So otherwise, the age of the account is a very good feature, but if we have an additional flag, which says, is this person dead or alive, that kind of helps our algorithm. It actually does. I mean, I'm sorry if it sounds like a joke, but it actually does. So the other one that we look at is basically we are tracking the amount of ATM withdrawals, across their. Yeah, please. Yes. Yeah. So the other feature that we also look at is how much of the the money that gets moved around, or that gets withdrawn is actually from the ATM itself. And the third feature basically is the average volume of money that we withdraw, that the person withdraws per week. And the second and the third feature is actually tracked for about 6 months. So it's not, if you were to track it for 1 week, it's not necessarily providing us enough signal for the algorithm to pick up. So once we track it across 6 weeks, I mean 6 months, sorry, in this case, it provides a lot of signal, to say, hey, this is how his usual behavior is, but what is happening probably this week or 2 weeks ago is not necessarily in alignment to what his behavior is. So I kind of briefly explained about how the age of the account itself is. So this is actually the #1 flag that the investigators use to identify, whether an account is good or not. The age of the account helps them identify this really well. And yeah, new accounts tend to do this, tend to do fraud a lot more than old accounts. And we did test quite a lot on this data set. And we found out that the age of the account is a very good feature, apart from that one odd case that we spoke about earlier. And the idea with ATM withdrawals and the all withdrawals is you tend to have a certain follow-up ratio that you do. So if you're more of a physical cash person, then you tend to draw a lot more. From the ATM, you tend to have a higher ratio because most of your transactions are happening through money, and not much of your transactions are happening in any other forms other than money and physical money. I mean, but if you're a kind of person who operates usually with cards, then this ratio tends to be really low because most of your transactions are happening non-ATM than anything else. So the idea here is that if we can track this behavior historically, then we are building a profile about you. Actually, I should take that back. We are building a profile about people like this. I don't want to be identifying one specific person. And that is what we use as a feature. And any spike in this feature kind of leads us to believe that there could be a money laundering situation. The average volume is actually another interesting thing as well. But we do see more than the second feature, the third feature shows a lot more outliers than the other ones, because sometimes what happens is, there are situations where you tend to withdraw a lot more money than usual, and it is actually for the genuine reasons. So we tend to see some more behavior in this, which is actually one of the reasons why this feature is actually ranked much lower than the other feature in a feature order list. But the idea of average volume of withdrawal per week for the tracking it for the last 6 months is that it's kind of similar approach where you have a certain behavior in moving your money, and if you were to spike it at some point in time, then the algorithm is comfortably picking it up. So now, rule-based systems tend to flag transactions based off usually one feature. Like, it's like, oh, are you withdrawing more than 2,000? Are you, depositing more than 5,000 or something like that? The issue with that is, as I've said multiple times, the signal, you have a very limited signal in that information that's coming in, because you're looking at one feature. And the idea that we go with is we go with a set of features that can help us move towards a certain, certain focus of the quadrants, more towards true positive, more towards false negative, false positive, or true negatives. And the advantage is once you use a lot of features, that tends to happen. In this case, we actually use close to about 450 features. So we use about 450 features in which we could track the ways money is moved, location, the unique ways in which we can identify a group of people. One of the things that we also strongly focused on is not to be able to identify anyone specifically, because that actually is very important to not be able to pinpoint someone. That is actually the job of the investigator to go say, if there is a certain probability outcome that we get out of it, the investigator reads that and then goes and investigates the account. It's not, yeah. So yes, the one limitation of this is although we predict, the investigator has to follow up with us. But the idea is that we run this on a periodic basis, for example, every day, every week, and the algorithm gets retuned, and the investigator gets to verify if the algorithm is working in the way they require it to be or not. So it's kind of the validation process that we use. So the combination of all these features actually uses a probability score of the event, and if there is high enough probability score, then we would predict that there is a potential money laundering situation. But mind you, there is no way to validate a money laundering situation, at least at this point at a bank level, because it's only the government that finalizes if a case that you raise is actually money laundering or not. So that kind of limits the visibility that we have. So this is just a brief introduction into how we use H2O and feature design for money laundering. Any questions at all?
Just maybe not related. What is the interest of financial organization to look for money laundering? In such a case, let's say this is a bank. They would lose clients. If my bank is the best in the world from money laundering, I will not have rich clients.
Yes, you're absolutely. I think you're absolutely right. We have repeatedly found that doing this kind of things is a cost center for financial institutions. It's not a profitable thing at all for them. Yes, it is totally unprofitable. But they have to do this from a compliance cycle. Yes, from a government regulatory compliance.
So back to your explanation, it's very hard to validate the results. How do you know what performance that you are?
No, it's not hard to validate results from the final, if the case was actually accepted or not. We validate it using what the investigator thinks it is. So our validation stops at the point where the investigator thinks this is potentially a money laundering situation or not. Because the government never sends us feedback.
Investigators still it's their guess. It's not.
No, it's not. It's actually a very educated input that they provide to it. So then it's not like let me guess this. They actually know how this behavior happens. So what we do is we're giving them a leg up.
Is it possible for you to develop a strategy to combat against this issue?
When you say security, can you be a bit more descriptive?
Like your strategy. You develop a strategy against this.
Against this? I wish I could try. Yeah. Okay, so we looked at different factors, and one of the reasons I chose a set of examples is because a lot of the features are actually sensitive as well. So, but we look at things. So we look at things as a time series. We look at a lot of features to see if we can replicate them as a time series. So time is a very core component of every feature that we develop, and we use spatial identification as well as another means. So we use things like how much money tends to move in your accounts. What is the periodicity of how you move money? What is your movement pattern? Are you a world traveler? Are you just in one place? So these are the broad areas under which we design features, but under each of these we design multiple features. Yes, yeah. We did have to reduce to a point where 450 makes sense. I know the number doesn't make sense, but someone here had a question. Yes.
It's just about how reliable is data. You could have a data set that's full of money laundering, but it's not been identified.
So at this point, across the globe, the only labeling that we can get is by investigators. And these people are experts in this field. The only thing is, it's a purely manual process.
So is it anomaly detection?
I would not go to the point where it's anomaly detection, because what you're trying to do is we're actually trying to. There are actually specific behavioral rules under which money laundering can be identified. If it would be about anomalous detection, then you would be looking at a different set of patterns, not just evading rules. You would be looking at things, that look extremely, common and not suspicious, but then that tends to be suspicious.
Do you work with one investigator or multiple?
Okay, that's actually a very good question. Because if we work with one, then we would have a super amount of bias. So we work with multiple investigators across different geographical regions. Because that across North America. Yeah.
I have a question about this looks like your workflow is you flag, machine flag some case, and then you validate that.
Not all the cases.
How about those unflagged one or non-flagged one? If you use the manual one to verify
So the ones that are not flagged, so you're looking at basically false negatives, right? So one of the things that we have to do is we have to maintain false negatives under a certain threshold, which is actually acceptable. And we maintain it at that level, which kind of makes sense for the bank. And while you're filing your SARS, it's called SARS, by the way, suspicious activity report. But you're filing it to the government, they kind of have a threshold below which if you can keep it, it's okay. So that's what we maintain.
So it's a follow-up phase. So your system is more linked aggressively, like people.
Actually, it's the other way around. Because one of the things is, as I was just mentioning, it's these kind of systems are a cost center for the bank, and this could you could lose customer loyalty as well. So you have to be super aggressive to not flag someone, because of suspicion. You have to have enough evidence. So we actually have a very high threshold to flag someone as doing money laundering. Yes. Oh, very good. Credit card is something that I've worked on, but not here. I mean, 4 years ago or so. No, not insurance, but we've done some other kind of fraud in insurance, not necessarily just like filing wrong insurance. I'm guessing that's the area you're going for.
So how real time is your detection?
It's about a day old. Like right now, the process takes about 3 to 6 months. With this approach, your timing can be about just a day.
1 day.
1 day you can come back and you can flag again.
So my question is not related to reporting, but it's more. There is a similar case from the 2016 India demonetization case. So in that case, what happened was there were millions of people who deposited $5,000 in their accounts, but that was the same for they were put in this scrutiny by the government. But there were a lot of millionaires who used poor people for actually get zero rupees in their account, and so they used poor people. Like a lot of unofficial millionaires used those poor people as money mules. So in that case, they also deposited $5,000 in their account. So how would we classify these two cases with all these?
So if you actually carefully observe how this process works, there is one, the depositing part, and then the withdrawal part. The depositing part, I completely, just ignored it, and I spoke just about the withdrawal. But this actually has two components. One is the deposit aspect and the withdrawal aspect. So the deposit aspect is where those kind of accounts would get flagged. You don't necessarily have to look at a withdrawal. You could train your features to just look at, is there a super high deposit that's coming into the account, out of the blue, and that should help you flag with a higher amount of probability. Yeah.
So the AML process is actually composed of 3 steps, like the placement, which is to get the money into the financial systems. This is like the most effective part.
Yes.
And then the layering, which includes the transfers from account to another
Yes.
account. and then the integration, which ends at the withdrawal of the money.
True.
I think, like, I myself worked on this problem from the graph database, from a graph databases kind of perspective. So have you tried the graph algorithms in order to solve or tackle such an issue?
We have not, but we are actually looking at it. Well, baby steps is what I would say, but we are looking at it. Yeah. Yeah, we specifically made sure that we did not segregate these kind of customers, because there could be someone. I think someone here. You had a question about anomalous behavior.
Just
Something similar to that, if I'm right.
A lot of positives in your data set that haven't been flagged.
Oh, okay. Because what I was the point I was trying to make for you was that there could be a lot of personal customers who are operating like a commercial bank. I mean, a commercial organization. And that's where, that's another group of customers we tend to flag. But we don't necessarily flag them as potential money laundering. We just say their behavior is not necessarily consistent with personal banking. So we actually group all of them together to see how the general behavior can be.
In terms of, you said that you were actually the time series models. When you're actually summarizing the data, and then running a classification on top of it from the summarized features, or when you're actually looking at the trend, since you said time series,
we were looking at trends, yeah. We were looking at seasonalities. We were looking at trends. When you say hardest, so we didn't. So for this, we actually used distributed random forest, which is actually out of the box for H2O. Yeah, and so the way we encoded the time series was we encoded it as seasonalities. So that's what we did. If that helps answer your question. Are you interested in joining? It is. I mean, so at this point in time, we've just hopefully done a good job. So we'll probably improve it soon. But I would be more than happy to talk to you if you've got some ideas. You can talk to some of the members in our company over here. That'd be great. Yeah. Thanks. Please. The volume. Oh, right. So one of the things is because H2O is perfectly cut to do these kind of things. It can move a lot of data, and it can process a lot of data very quickly. We have like hundreds of gigs of data. You can just use H2O and do it. But if you're trying to do the same thing with scikit-learn or something, your machine will probably fail. You can use Hadoop as well. Yeah. So in this case, we use Spark. So yeah, so what we did is we also have another product which is called sparkling water. You might have heard of it. So we use sparkling water in this case.
So in this case, data volume is big.
Yes, yeah. Because one of the things that we have to look at is we have to look at transactions, right? So it tends to be really big.
So after creating a feature, you said you're using random forest, right? So, but what is it training data? So I assume that only governments know whether an account was money laundering account or not.
Okay.
Doesn't know.
So the training data set that we use is the ones that the investigators have already flagged, because for any non-government organization, the last mile is the investigation, the data that's being hacked by investigators. You can never get visibility into the other side. At least that's what we've got to know. So we use that as our training data set. Okay, so